All right. So we're very happy to welcome cohort 3 of the Community for Rigor Community Virginia Tech team, led by Dr. Alexandra Hanlon. They're going to do a short presentation, and then we will continue doing cohort 1 presentations. So welcome.
Thank you so much. Thanks. Can you guys hear me okay? Yeah, so I'm Alex Hanlon. You can't? Tanner. Okay, how's that? Awesome. So my name is Alex Hanlon. I direct the Center for Biostatistics and Health Data Science at Virginia Tech. We are geographically located in Roanoke, which is about an hour north of the main campus in Blacksburg. We're super excited to be with you all. I'll give you a little bit of background. We've got 5 minutes. I'm not going to keep you long. I'm going to take about a minute to introduce you to my team, and then they're going to take it from there. So I came to Virginia Tech actually from Penn, where I built this collaborative group, which I've been doing throughout my career. I am a collaborating biostatistician. Started out in cancer research for very personal reasons, and basically have studied best practices for collaborative groups for a long, long time. So at Virginia Tech, there was no collaborative biostats. There was no biostats at all in 2019. But then we have a relatively young school of medicine. We had our first CTSA award, which requires, of course, the Bird Research Methods Cohort, et cetera. So we needed a center. Alicia came with me here from Penn. There were 2.5 of us in 2019, and now with students and all, there's anywhere between 15 and 20 of us. So basically, the idea is that we're there to work and facilitate excellence in scholarship within the health sciences in general. So there's that. So here, I don't think the animations are working, but this is our team today. Is it working? Yeah. Woohoo! Okay, so this is our team now. We are biostatisticians, data scientists, bioinformaticians, statistical programmers, epidemiologists. So I'm very proud of this group of people right here. And this group in red, these are the folks that are really integral to the initiative that we're talking about today. Okay. Ta-da! That's it. Thank you.
So as a group, we'll be covering 3 topics for our educational units. And so the first one is, of course, creating statistical analysis plans, or SAPs. And then we have 2 on bias. So one covering selection bias, and then the third measurement bias. And so our motivation and why we wanted to come into this was because, as Alex explained, we are collaborative biostatisticians and epidemiologists. And so, of course, we're in Philadelphia. I have to take Sylvester Stallone. And so Rambo quote, "This is what we do. It's who we are." And so, yeah. And then as far as our educational unit goals, and of course, the overarching goal is to promote rigor and reproducibility in research. We want to provide our learners, obviously, with skills in creating formal plans, as well as various key strategies to identify assumptions and sources of error.
And that was Alicia Lozano. Yes.
Hi, I'm Rachel Silverman. So I'm just going to go through a few of the details about our units. So we'll be doing one on statistical analysis planning. So what information is needed to get started in developing a useful statistical analysis plan, what actually you need to know and what you need to do this and why. And then at what point would you need to involve a statistician and how to interact with statisticians to help with this process as well. The bias units on selection bias and measurement bias, I'll be leading those on the epidemiologist team, but with help from everyone. And so thinking about in both of these cases, what are the limitations when selecting comparison groups when you're doing analyses, thinking about the selection criteria and how that can impact your studies, and then focusing on like measurement error, differential versus non-differential measurement error, how that can infiltrate a study and what to do about it, how to prevent it, and what it means in terms of your inference. So ideally, in both of the, in all of our units, we'll use real data sets, real examples to illustrate and reinforce these concepts in an interactive, engaging way to really reinforce this. And so we hope that the statistical analysis plan will draw on the existing units from all of the meters as much as is possible and feasible. And thinking about the demonstrating the negative impact of science when you're not doing a strong or any statistical analysis plan. Thinking about the biases, demonstrating how to prevent, correct for, and identify and understand selection and measurement biases, and how these can creep into your study and impact your results. So, okay, I think that's all we have.
Should we go ahead?
It's always blinded by this little thing here. Well, hello, everybody. As most of you know, we are the team from Johns Hopkins and Virginia Tech, the other Virginia Tech involvement that we have, quite a bit of a heavy representation. Definitely, in this case, the Blacksburg campus. And I'm from the Bloomberg School of Public Health. Our team is actually, apart from Aparna and myself, is composed of Dr. Turo Casadeval, the chair of the department where I work in the Bloomberg School of Public Health, as well as an assistant professor in our department, Dr. Yotham Suez, as well as Calliope Holling from the mental health department at the same school. How do we handle this? Okay. Yeah, very obviously, right? Don't need to introduce ourselves, but generally we are producing two units that are rather fundamental. One that looks into causality versus correlation, particularly in biomedicine, and looks, in general into questions in the biomedical sciences, describing correlational and causational relationships, terms and definitions. And then, of course, very much looks into those concepts by applications to, general examples that everybody can relate to. And we also think about, sources of evidence, how to build stronger evidence overall for a case by a combination and triangulation, as well as ways to evaluate causal evidence.
And just reintroducing myself. So I'm a collegiate professor, which means my role is predominantly teaching students. It includes undergraduates and graduate students. And at Tech, we have a School of Neuroscience with 4 neuroscience majors for undergrads. So I'm looking forward to testing all the material with students coming from different neuroscience backgrounds and motivations as well. As far as my unit goes, it's focused on the importance of controls in experiments. And so, of course, talking about experimentation in scientific research and its significance first. And then if you talk about controls, you need to introduce variables. And so that will go into the longer version, but perhaps serve as a glossary for all units, and then focusing on controls and how they're important at every stage of the research experience, whether you're designing your study, troubleshooting, or interpreting someone else's study. And that goes hand in hand with validity of experiments, and something that would make it logical or practical is to talk about challenges when implementing controls. So not keeping it real, not just making an ideal case for controls. And then something that is really interesting and fascinating to me is placebo effects, and that goes into human research. And so we've been talking a little bit about including that, even though that may be a little bit of a stretch from the preclinical research that I'll focus on for the first part, or the animal research and other models in the first part.
We were asked to come up with a couple of thought processes and that illustrate the way how our thinking was in order to develop these units. And rather to go into all kinds of details, we were thinking a little bit from a high level about those things. I mentioned the first of the units goes very much into the concepts, right? Because this is something that we learned from teaching this in some of our own students, that the concept of causation is something that's not easy for learners, neither for the younger ones as well as for the more experienced practitioners. There's a lot of mistakes coming, and that's the reason why we started with a very conceptual unit. And we bring a lot of real-world examples and allow learners to learn from misconceptions as well as from natural phenomena that are something that is very kind of obvious for everybody, right? And then there will be, for the more advanced learners, there's examples for the neuroscience in there, but we start with something that's very basic that everybody finds tangible and approachable. And some of the examples, I'm not going to go into those in great detail. Happy to talk later about them, but we don't have so much time now. We look in, for example, in historic examples. There's an example about 100 years ago. There was a epidemic of polio outbreak in San Francisco. It's a real world example. And the public health officials at that time were not informed yet how the transmission of polio would work. And they correlated it with those particular outbreaks in San Francisco with the popularity of ice cream trucks at the time, right? And then they forbade the ice cream trucks, right? And this allows us to come up with an example of how a misconception about a certain correlation can lead to a false causal claim, right, in this case. And it's quite nice for us to introduce variables, confounders, and the visualization exercises that we will also demonstrate in Chicago at this SFN. Then another example comes from, for example, flu shots. It's a common belief in the population that you have all probably heard that, oh yeah, I got the flu because I got the flu shot, right? Well, you feel, of course, the immune system reacting, but this is a very common belief, right? And this is another way for us to allow the learner in a very tangible example to learn from, basically these misconceptions about the causal claims, as well as the miscommunication of causal claims, right? And another example that we also bring in here is, for example, the lunar tide effect. Everybody knows that, right? Since like thousands of years, maybe 10,000s of years. And this allows us to look into what kind of types of evidence are there available to support causal claims? And particularly, what do you do if you cannot do experiments, right? If you only have indirect experiments. When you look at the lunar tide example, all you have is indirect experiments since thousands of years, right? Observations, then multiple observations. At some point, you have inferential observations when you had, better meteorological instruments. And then, of course, since a couple of years, a couple of decades, let's say, you have predictive analysis through computer modeling, right? But none of them is a direct experiment, because otherwise you would have to remove the moon, right? And so this is the problem, right? To show like what can we do in order to make causal evidence better by accumulation of indirect experiments. Yeah, and I'm going to leave this out now, but at the SFN, we are going to visualize those through a couple of exercises that have to do with directed acyclic graphs and other communication exercises.
And I decided to focus a little bit on the target skills to share with you folks today. And so, of course, selecting controls or acknowledging the importance of controls is one thing, but selecting appropriate controls is a really important concept that I chose to focus on in the unit, of course, with the help of Senda and the brainstorming with Gunilla as well. So the other aspect that I chose to focus on is limiting inference based on the controls that one has. So in some sense, acknowledging that an experiment is not a complete failure, but how you interpret it depends on the design of the study itself, and the result statement should really reflect the experimental design. And then overall, I try to keep the examples realistic, and I've had decades of experience working with different model systems, which is what I'm pulling from in addition to literature. And I believe I mentioned the 3 stages already for the learner, and some takeaways, again, focusing on the appropriateness of the controls. There's no perfect design, but a good experimental design is one from which you can learn something, and that it's important to acknowledge limitations that stem from the choices you make and the power these choices have. And then
you want to start with that, actually?
Sure.
Actually, yeah, right. Yeah.
Right. So, I mean, this is some personal reflections here. One is related to the impact on teaching some of the courses that I teach at Tech. So one is a senior seminar where students look at primary literature. And so I'm really having them focus on looking at the kinds of control groups and the decisions that the researchers have made and reflect on why they may have made those decisions, appreciate the nuances in those choices that researchers make and how that can make or break the interpretations. And for my personal thinking, now that I've moved from wet lab research to scholarship of teaching and learning, as a collegiate faculty member, I am trying to think more seriously about rigor in these sorts of studies, which includes, I guess, the meta, the studies that we're doing with C4R.
Mm-hmm. And we also, in our common reflections in our meetings, actually always found that early on we should include those exercises, even if it's only a portion of what we are developing, into our educational practice and really learn from our own learners, right? The way how it goes, and do this early on by learning from how does it go in the classroom. I very often underestimated the time I need for those exercises. I learn a lot with and from April, because April has a very structured way of looking at my exercises. I tend to be jumpy, right, and do this, in a very high level. But April says, well, we need a little bit of a step in between, right, because the learner needs to be guided from A to B to C, and I quite often jump from A to C or D, right. And this was very helpful for us to have the communication with other educators with Center, and also from our own learners to really understand how much time and what it takes to really implement the exercise, right? And I learned this from a causation class that I teach in my own institution, as well as from a collaboration I have as a high school. And there I actually used the lunar tide example, and they were thrilled. It was something that really worked, and it showed us that also abstract concepts like causation can be brought to life in a community for people under 18, right? And give them really a strong correlation, a connection with the topic. Yeah, I think, and there's just some last steps, but it's essentially what we said before, right? Next step is what we were asked to also reflect on, really again to bring this very, very early on into the learner community, and include the same rigor concepts that we include for the way how we try to do science, also to the teaching and the scholarship of science, right? Mm-hmm. So this is something that we quite often see is a big issue. When you try to figure out whether something works, right? We need to include the same rigor standards also to the way how we evaluate those in the educational community. Okay.
From us. Thank you.
So while I invite Mary from Smith College, I'll remind you, if you have any questions that pop up while the meters are presenting, please, jot them down or keep them in mind. We'll have a short 10-minute feedback or question session after the last meter. Go ahead.
Thanks. So I'm reporting for my team that includes Lisa Maggiamelli and Sharon Owino. We have been working on 3 units. The first unit we worked on for the first year, which was an overview of the research process. I'm going to tell you a bit about that. And then the next unit, we thought the first unit turned out to be probably the hardest we'll tackle. And so we moved to what we thought was the simplest, which is the randomization. And that one we'll see more about throughout the meeting. And then I'll tell you a little bit about the unit we're still developing and really enjoying, which is setting exclusion criteria. We sketched this overview of the research process as we thought about that first unit. And in fact, I use this in my teaching as sort of a touchstone. And I think it's really helpful I'm teaching undergraduate students a course on experimental design. And to be able to say, and here we are today or this week, we're going to all focus on this part, but to sort of root students in that there are many places where we're going to talk about the need to be rigorous. And our idea for this unit, for this group of learners, was to make it very self-reflective, to offer students opportunities to try out their abilities at different skills within these little categories, and then give them a chance to reflect about where they needed more development and help them build what's really like an individualized plan through all the units, for them to be pointed to, by their self-reflections, here's where you probably want to go, and then link to the other units that are produced. So I still think that's a good idea for people to make their own plan for education and professional development. The unit that we then moved to create in more detail was one on randomization, because this is, of course, a key principle, and our students all know you should randomize and then don't do it. And I think that often they don't know how to do it. So our idea here was to give them good, concrete understanding of how randomization can protect you from bias. And then we thought experience in writing R code that would allow them to randomize well. And then some experience with different types of randomizations. So simple randomization to start, but then to begin to realize, oh, I might need to randomize by various other variables, confounding variables. To move to block randomization and other types of randomization. So we thought of a progression of units that move from simple skills to more complex skills would be helpful. And as we thought about this, we wanted to be inclusive to the learners, and that in many cases, the examples from clinical trials, people who are students who are working with animals might think, well, this is totally different from what I want. And the examples from animal studies, vice versa. So we wanted to mix up our examples. We actually thought in many cases you have so much more control in some animal experiments, and so it is a very different setting. And we wanted people to think about both examples. Here's some of our first ideas. We had, I don't know, pink people and blue people. And we were thinking that you need to distribute these people of different colors in these different groups. And you might need to talk about, this is from our initial thoughts about block randomization. So we're just thinking together, how would we talk about basically you're taking your big experiment and blocking it into smaller groups and then distributing your variables across those groups. And then we found this is stolen off the web somewhere, someone using R to illustrate block randomization. And then we're like, cool, there's some R code. And then we had office hours with April, multiple office hours with April. And that really helped move us forward in a really positive direction, I think, where we were able to start visualizing with April how this could be made much more engaging. And you will all see more of that. This is one of the units that I just got a vision of it, which is really nice. And this is the vision we're working from, where we're thinking about what are the steps of the learner through this, and April's working to design the web pages, the visualizations, and then we start thinking about, okay, when do we want a slider? When do we want people to actually be able to modify the code? And in fact, she's building things where you could modify the code, or you could just use a slider. And I think that's brilliant, that people have different abilities, but we really do want to have people feel like they're walking away with some skill. So you will see more about randomization. I'm pretty happy with that unit. Finally, I'm working on an exclusion-inclusion criteria. Both inclusion and exclusion criteria are important. And this unit, I should also shout out to Hao. He's helped a lot in the shape of all these ideas. But this unit really, I think, has benefited a lot from Devin and Mariah and Shai's input of specific examples. So one example that I really loved was an example of researchers working on ALS and using animal models. And there's a very, very important key animal model that has several really important variables to that animal that need to be used for exclusion-inclusion criteria. And researchers who weren't doing that were producing a lot of data that's supportive of treatments that are not useful. And so here you see a real-world example of treatments being applied to people with ALS in a rushed way, because we really need treatments. And in fact, they're based on very flawed research. It's to the level of like not checking the genotype of the animal in the way that it should be checked. that some animals have multiple copies of the gene. So maybe more detail than you want, but I love the detail. And what I also love was that the researchers shared a full data set of animals, the control animals. So this was a rich data set because we can then use that as we build our activities. It's real data. The animals, this is a real range of, in this case, longevity of the animals being used in these studies. But if you don't consider carefully the criteria for inclusion or exclusion, you will come up with spurious results. So we haven't built that yet, but I feel like I know what I'm doing there. And the thing I'm really open to is if any of you have examples. I feel like if a student's head or a young PI's head is filled with examples of cases where instead of throwing out the outlier, they looked at it and learned from it, that's going to be really helpful, and that we should have more anecdotes that we create really engaging examples from. So the one that's current in my life is with it, I'm thinking a lot about Alzheimer's disease, and people who carry the APOE4 allele are at higher risk for Alzheimer's. And a newish study came out saying, yeah, but some people carry 2 copies of that allele, and you would think they would get Alzheimer's, and they're like 90 years old and smart as a whip. And what is going on in them? And they carry another gene that protects them. So it's super important that you look at that outlier, the people who you think, well, they just don't follow my rule. Then you look at them. And Mariah gave me the example of the paper that years ago was published where they said, this is how you define an outlier. And that paper went on to say, and what you do with that is you then look at those cases where I think I was taught this is how you define an outlier. You can throw it out at that point. And so I would like to add some engaging examples of why your research will be enriched if you study those outliers more. So if you have examples, please let me know. And that's it.
All right, hello. I'm Michael Gianfrido. I'm here on behalf of the Duquesne team. My colleague Jordan Covey couldn't be with us today because she's teaching. Also, Melissa Kalarchian, David Nolfi, and China McClendon are part of our team, and they couldn't join us, but I'll try to do my best. It also says Mayo Clinic because in March I moved from Duquesne University in Pittsburgh to Mayo Clinic in Rochester, Minnesota. So we have 3 units at Duquesne, and it's really getting, at least the first unit is really getting back to the basics here, which is how do you formulate a valid research question? And so Jordan and I, for example, often work with students that these are pharmacy students. They haven't done a lot of research before. And so they might do a research rotation with us, or they might do independent research with us for a semester. And, we talk to them about research questions, and the ones we get back, they're often missing something or they haven't really thought through it. And so how can we really help students think about how do you best elaborate or specify on a research question so that it has all those pieces that you need, right? The who, what, why, and how. And we talked about this last year, and there's different frameworks for specifying a research question. And in the clinical realm, you might have heard of PICO, for example. But it's getting at the idea that, what exactly is it that you want to study, and clarifying and specifying that. And then once you have that down, how do you then evaluate that question to see, well, is this even answerable? And so we use the FINER framework. And if you haven't heard of the FINER framework, is the question feasible to do? Is it interesting? Is it novel? Is it ethical, and is it relevant? So by the conclusion of the unit, through the didactic portions and through the activities, ideally someone can construct a research question that has all of the necessary components and you've thought it through to say, okay, I can actually do this with the resources that I have. It's interesting to me, it's relevant, right? And it's novel, et cetera. So that's the first unit. But then, we were thinking also about, well, one of the things in the finer criteria is, well, how do you know if something is novel, for example? Well, you have to go to the literature, and also going to the literature might give you ideas for questions. So how do you actually search the literature? You could just type in whatever pops in your head into Google. I mean, maybe you can do that, or you can ask ChatGPT, but that might not be the most systematic or appropriate approach. And so how do you think about building a structured search that's going to get you what you want? And so building those searches using tools like keywords, index terms, and other advanced functions like truncations or phrase searching or field tags or filters or things like that. And so walking students through how, for example, do you use PubMed well so you get the results that are applicable and you get less results that are not applicable to what it is you're actually looking for. And then again, having a framework or structure to evaluate, well, did I construct my search well, or is there things that I've messed up? Even me, when I construct searches, sometimes I mess up my parentheses and my Boolean operators and I get something completely screwy. So, right, taking the time to go through and evaluate that. And so giving students a framework for, okay, once you've constructed something, how do you then go back and look at it, that reflective practice? So after the 2 units, right, they have a question that they've worked to develop. As they develop that question, or before they develop that question, they have the skills to go to the literature to maybe get some ideas or to see what is the gap in the literature. Is this novel? And so there's this crosstalk between the 2 units. The last unit is you've searched the literature now and you have a body of literature. So this isn't about a specific paper, but once you've got, okay, I did my search, I got 20, 30, 50 results, whatever, and I've read these papers, how do you make sense of that? And so we've adapted the grade framework to think about how do you look at a body of literature? How do you know whether it's credible or trustworthy? And thinking about what are the study limitations? Are all of my studies randomized, right? Are they all high quality studies? Do they not have limitations? All studies have limitations. It's just how much does it sink the reliability or validity? And so talking to students a way to think through that and giving them examples of checklists that exist out there to assess, for example, the risk of bias. Then looking at things like, are your results all consistent in your set of data that you're looking at, or is it inconsistent? Do some studies say, ApoE is protective? Do some say it's harmful, for example? And what do you do with that information? Do you have, someone else was talking earlier about direct and indirect, I think with the causality, right? What does that mean? And how do you interpret it when for your particular question, you have direct versus indirect evidence? How do you start to interpret that? And then imprecision, which gets at the statistical issue here, right? Do you have wide confidence intervals or narrow confidence intervals in the results? And what do you do about that? And finally, we introduce the issue of publication bias, which I think will be touched on in other units, but we mentioned that idea. So as part of this, there are various activities for the sake of time, just highlighting, for example, one where we give students examples of a research question and ask them to rate it. So for example, is a question good? Is it better or is it even better? And so the reason we did this sort of framing, and I don't know where Karen is, but I think the rating, we might have used a slightly different scale now, but the idea is not saying this is a bad research question. We didn't want that kind of framing, but be able to show how you can better elaborate on a question or add potentially additional details to make it, okay, well, this is much more clear now. And so compare their answers to the cohort average, so very similar to what we did today. And this activity occurs in the unit prior to the content. So we say, okay, what's the baseline? And then we're going to teach you and then see if you get better at identifying good questions. The learners are also asked to provide written feedback on the strengths and limitations. So for lab unit versions, you can say, well, I liked how they did this. I liked how they were very specific about the model or the population, but I didn't like this. And then in a lab, you can discuss, well, what would you have done differently? Or how might you improve this aspect of the question? So on the process, you know, we, Jordan and I regularly teach these topics. And so, you know, this is something, like I said, we see a lot. And this project has helped us think about how we teach these topics, especially how this impacts down the line and the rigor of research. So how is it that creating good research questions is ultimately going to produce better research? So it's made us really rethink about how we kind of emphasize that as part of the teaching, and made us realize the power of, you know, the language and the framing of specific concepts and how that has the potential to change, you know, the meaning and interpretation of what we're trying to get across. And so with Karen, we've worked a lot on language and for example, the positive framing and talking about, well, it's not really a bad research question per se. It's how do we make it better? And so we've had those discussions, for example, with Karen. And so the next steps for the final year is really to work with Center to refine developed content and activities. And I think that's it for me, and it's up for Harvard.
Last. All right. We're already behind time. So, and least. All right. So first, here's the team. They're all here. I see David raising his hand in the background. David, you were raising your hand? Oh, okay. All right. All right. So we have Ella. And the notes are here, so I can actually look at my notes. So Ella is currently the assistant director for educational programs at the Kempner Institute. And the Kempner, all you should know, is an exciting new institute at Harvard designed to study biological and artificial intelligence. So Ella's leading the educational group there. Tari, who is the assistant dean for educational innovation and scholarship at Harvard Med School, and also a lecturer in the neurobiology department. And finally, we have Jade, who's, actually, and Ella and Tari are in the middle table there. Ella's on the right, my right, Tari's on the left. Jade is right here. Jade is the inaugural Rigor, Reproducibility, and Responsibility Curriculum Fellow at Harvard Medical School. So here we go. And that's me in my better pose. All right. So I think I construed Thomas's instructions a little bit differently from the others, so bear with me here. But so these are the 4 units that we proposed in the state. So the first 2 are, I put complete in quotes for obvious reasons. Ella and I have sent a whole bunch of stuff to Center, and they're working furiously on them, and we're still involved in refining those materials. The third one, distinguishing experimental failures from biological answers, has phase 3 submitted. And this is the least developed so far, detecting errors in your analyses. And I'll have a little bit to say about that in the last slide. But we were asked, what I did is I made my presentation around what I want 2 lessons to be taken away, hopefully, especially by the cohort 1 and cohort 2 folks. So this is one of the specific aims of our proposal was on bias circa 2022. And this was one that I was primarily involved in crafting. Yuri and Mark may recognize this little thing here, which I stole from their book. Why can't I point to it? Can I go? There we go. This thing here. It's their Poisson point process analysis exercise. But in this case, it was an example of omitted variable bias. So I was going to cover bias because they don't have the direction in which the rat's running in this model. And so the model has big residuals in one direction and negative residuals in the other. So anyway, I was going to cover measurement bias, confirmation bias, bias in general, model bias, all sorts of things. And of course, we rapidly realized, and this was through discussions with Devin and Shai at NIH and with the steering committee and with Center as a whole, that there's no way that this could make a really effective teaching module given what we wanted to do. So lesson one, and I think I saw that in some of the initial presentations, there was a lot in some of them, especially the first one, right? There's a lot there. And so you're going to have to really focus it down and focus on skills and activities that you can do. So that's lesson one. Lesson two, they asked us to pick. This is what we eventually honed this unit down to. And then Thomas asked us to pick one. Oh, that didn't work out. Well, whatever. It's supposed to be, the red thing's supposed to be down here. And it was an example of an interaction with Center that you felt like worked and got to a better place. So I'm going to pick this one, How Good Is Your Mask? And really, I sent a bunch of stuff, I read a ton of papers and I knew this literature inside and out. But in terms of an activity for this unit, this was as good as I could do, which was I had this little, joke slide and a goal. And my goal that I think I articulated to Center was to get students to really think about ways in which blinding can fail. Right. And it's amazing when you read the literature. In fact, I have a friend who runs a biotech hedge fund who's made millions and millions of dollars off of figuring out where blinding has failed in studies, clinical trials, and where they got a false positive result. And he short sells them and he makes lots of money. So this is a real thing out there. But anyway, so that was my goal, but I didn't really have a good activity. Well, after Ani joined the team, I get this email from her. And I think it was sometime, where was it, like in April or May or something like that, Ani? Very recently. And she says, Rick, we designed an activity called the Rigor files that springs from your ideas about tells. And tells are the things that the dog wagging its tail is a tell, right? They say even the best professional poker player has 6 or 7 tells. That's why they wear dark glasses and try not to show any emotion. Anyway, so Ani sent me this, and then she sent me a bunch of questions. And I sent her back a kind of long, you're not designed to read all this, right? It's just to show that there was an interaction. This was all done over email. And then I said something, it's off the bottom of the page. It says something like, I'm not really sure if I'm answering your questions. And then Hal came back in and said, sorry, I could have specified more clearly, blah, blah, blah. And here's what we're trying to do. And then I wrote back saying, I think I get it now. And then I wrote a whole bunch more, right? Not important what I wrote. But, and the result is, I think, going to be a really cool series of exercises for the students to really engage them and get them to think about this important topic, which isn't very widely thought about, at least given the students that I interact with. And so the second lesson is use Center. In other words, I think this is a case where the interaction really led to something better than otherwise either one of us would have produced in a vacuum. And let me just end with a little bit of analogy. When I started my lab for about 30 years worked on alert non-human primates, studying their visual systems. And when I set up the lab, and for this kind of work, you constantly need gizmos, little devices that need to be machined or engineered and whatnot. And at first, I would sit down, I'd spend hours coming up with like the best design and everything. And I would take it to the guys in the machine shop. And they would look at it and they'd kind of roll their eyes and whatever. And after about, 3 or 4 iterations of this, I realized that the machinists had way better mechanical intuition and knowledge about how to build stuff. So I shouldn't go to them with a design. I should go to them with an idea, with something. I say, I want this gizmo to do X. And they would design a much better X than I could, or a much better Y to do X than I could ever do, right? And I think that's the case here. I've realized now that Center, people like Ani and Hal, they're much better at coming up with these sorts of things than probably most of us are. But I knew a lot more about the literature and had thought about all these different ways that blinding could fail. So I think the interaction is what really will make ultimately for a better product. So, and I think that's the way it should work. And having said that, I think Zach's presentation this morning about the 2-4-6 exercise, that also started with me. Actually, it started with Peter Cathcart-Wasson, the experimentalist who did this back in the 60s. But the idea to put it in the teaching materials came from me. And when I saw all the stuff he's learned from their focus groups, I felt like if they would have come back to me with that a little earlier, I had all the Cathcart original papers and how clear he was about explaining the exercise to the students. I could have saved you a couple focus groups probably. So there you go. Anyway, the last thing is just where we're going next. And this is a unit that Ella is primarily leading the charge on. And it really, the moral of the story is don't just click buttons without knowing what they do, right? And I think this is not, oh, it does show up. The sizing is a little whack here, but anyway, what she's going to do is focus on a real exercise that was from Roz Siegel's lab, where they're looking at axonal degeneration and culture, where the data is images of these cultures, right? And so there's a fairly sophisticated analysis pipeline that involves image processing. Right here, they're contrast reversing and probably doing some, and art, and then going ultimately to something that you can do statistics on, right? And I think the idea here is that our students are more and more using very sophisticated kind of off-the-shelf tools, but it's not always clear what's going on under the hood, and certainly choices of meta parameters we know can make big differences in analyses. So the goal here is to get students to think through this process and make better choices in their analysis. And that's it.
So yeah, talk about collaboration and doing things together. So thanks for that, wrapping up comment from Rick. Does anybody have any comments, questions for the meters that presented? No, all good? Okay. So we can go on a little break. We're very good on time. In 5-10 minutes, we'll call you right back. Thank you.